Alright, today we'll be talking about optimization. And in the simplest terms, an optimization problem consists of maximizing or minimizing a real function by taking the derivative of a set equation in a system of equations. For example, if I wanted to find the maximum product of two numbers that add up to 10, we would take the derivative of the product equation, not the one that's summing it. So that would be the set equation that we take the derivative of in the system of equations. And there's some real world applications of optimization, such as minimizing time on a trip, which even goes as far as like UPS when they talk about logistics and stuff. A lot of those are optimization problems that they're using. Same with productivity for pipes and other types of electrical circuits. Optimization is used to find the most productivity in that you're giving the most water or oil or electricity to someone for the least amount of product used. And actually in scheduling games for professional leagues like the MLB, NFL, NBA, all that, it's actually an optimization problem. Although it's not the same kind of optimization that we do here in calculus, and nonetheless it is an optimization problem. Alright, for our first optimization problem, I'm going to show you one of these most simple optimization problems, and it's usually a pretty good introductory one because it's a problem you've done in the past, although this time we're going to take a calculus approach to a typically algebraic problem. And the problem we're going to do is when the sum of two numbers, sorry, I write slower than I talk, two numbers is 10, maximize the product. Now I'm sure you've all seen problems like this before, in that whether it's just a challenge problem on a past homework in algebra or geometry or whatever it is, I'm sure you've seen this problem before, but this time instead of taking an algebraic approach, we're going to take a calculus approach to the problem. And for every optimization problem, there are 4 guidelines to solving it. The first one being that you want to write the function be minimized or maximized as a function of one or more variables. And in this, since we are maximizing the product, we're going to have x times y is equal to our constant k. The second guideline for solving optimization problems is that if your function has more than one independent variable, we need to relate the variables. And since the sum is 10, we're going to have x plus y is equal to 10. So that's how we relate them. The third guideline is that we want to be able to write this function right here in terms of a single variable. So in order to do that, we're going to have to solve this for y. So y is equal to 10 minus x. Now we can write this function k in terms of y, and we're going to do that right now. So we would have k is equal to, since we have x times 10 minus x, and now we have k in terms of x, not y, as I said earlier. I apologize for that. And our fourth guideline to solving optimization problems is that we want to find the critical points and then use the first derivative test to determine whether it's a minimum or maximum. And we find the critical points by simplifying this and then taking the derivative of it. So we would have k is equal to 10x minus x squared. Let's go ahead and take the derivative of that, and since k is a constant, it's simply going to become 0 is equal to 10 minus 2x, simply using the power rule. And let's go ahead and rearrange this to solve for x. So we'd have 2x is equal to 10, and then x is equal to 5. Now, since we know that x plus y is equal to 10, and now we know x, we know that 5 plus y is equal to 10, which means that y is also equal to 5. Which means that our constant k is actually 5 times 5, which is actually 25, which is the maximum of the two products.
Another useful application of optimization is to find how far away a point is from a graph and make it as short as possible. You can use this by using the distance formula, which is root y1 or y2 minus y1 squared plus x2 minus x1 squared. This is just a version of the Pythagorean theorem, and it will help us optimize the distance between the graph and a point. For instance, if we have a graph, for instance, that is y equals root x minus 8, and we have a point 12, 0, and we want to find the point on the y equals root x minus 8 graph that is closest to the 12, 0 point, we can plug that into this equation, which will look like this, where you have y2, which is 0 because of this ordered pair, minus y1, which if you plug in x here, it'll just give a y value, and we're trying to find that y value. So once we square that, we can find the x coordinates, which is x2, which in this case is 12 because of the ordered pair, and on the graph that we're trying to find, it will just simply be x, and then we square that as well. And this is our distance away from the graph to the point. Now, in order to do the optimization, we're going to have to take the derivative of the distance graph, or the distance formula that we have here. And once we do that in our calculators, d prime is going to be equal to 2x minus 23 over 2 times root x squared minus 23x plus 136. And in order to find the x value that will minimize that distance, we're just going to have to set it equal to 0 and solve for x in our calculators or by hand. Once you do that, x is equal to 23 over 2, or 11.5. Now that's only half of the thing because we have to find the y value that corresponds to that x coordinate. We can do this by plugging it back into our original equation, y equals root x minus 8. So whenever we plug that in, y is going to be equal to root 14 over 2, or just 1.871. So our coordinates for the equation that will result in it being closest to the ordered pair 12, 0 is 11.5, 1.871.